for AP Calculus on the topic of the second fundamental theorem of calculus. So recall that the second fundamental theorem of calculus is what relates the derivative and the integral. So if you take the derivative of an integral, as long as the lower limit is a constant, then they essentially cancel each other out and you're just left with the original function. The only difference is that x ends up replacing the t, but f is still the same function. So this example problem says the graph of the function f shown below consists of 5 line segments and a semicircle. And that g be the function given by g of x equals the integral from 1 to x of f of t dt. So for part A, we're asked to find g of 5, g prime of 5, and g double prime of 5. So let's start with g of 5. So to find g of 5, you would just look at where the x is and replace the x here with 5. So the integral from 1 to 5. Notice this is t, so we would replace that. So f of t. And we don't have the equation for f of t, but we do have the graph of it right over here. So you just have to remember what the definite integral represents graphically is the area between the curve and the x-axis. So starting at 1 right here, and going to 5 right there. Okay, so to figure out that area of this region right here, between the curve and the x-axis, we can split it up right here into a triangle. So let's find the area of that triangle first. If we take 1/2, the base here is 2, times the height is 4. 2's cancel, you're just left with an area of 4. And to figure out this region, what we can do is take the area of this rectangle and subtract the area of the quarter circle. So the area of the rectangle, the base is 2, times the height is 4, minus the area of the quarter circle. This is the fourth of the circle, it would be 1/4 pi. You can see the radius, if it was an entire circle, would be 2. So pi, the radius squared, 2 squared. That would be 8 minus, here 2 squared is 4, that cancels out with 4 and there, gives you just pi. So 8 minus pi is the area between the curve and the x-axis. So if you add those up, 4 plus 8 minus pi, you get 12 minus pi. So that's what g of 5 equals. So what we found is a point. The x-coordinate is 5 and the y-coordinate is 12 minus 5. Point on, not on the derivative, but on g of 5, on the original function. Next we need g prime of 5. Well, we don't have g prime yet, so let's start with g of x right here, and let's take the derivative. So to find g prime of x, that means we need to take the derivative of the other side of the equation as well, with respect to x. So it's the derivative of this integral from 1 to x f of t dt. And here's where the second fundamental theorem of calculus comes into play. So we can see the derivative of an integral fits the second fundamental theorem, and the lower limit's a constant, upper limit's x, so it fits it exactly. So what that simplifies to be, the derivative and the integral essentially cancel each other out, and we're just left with f, and now all that happens is that x replaces the t. So f of x. And remember, we have the graph of f over here. So what we just discovered is it's not only the graph of f, g prime is equal to f, so this is also the graph of g prime of x. So that's how we can figure out what g prime of 5 is. Since this is the graph of g prime, all we'd be looking at is where's the y value of 5. So see right here, the derivative of 5 is equal to 2. So again, we're just looking at the y value. Because this is g prime. Whenever the graph is the same as I told you before, you're doing this before. And finally, we need G double prime of 5. Well, if G prime equals f of x, that means G double prime would equal f prime. So G double prime is the same as the derivative of f. So here's f right here. So the derivative of f represents the slope. So to find G double prime of 5, you look at the slope at 5. Right there, you can see it's got a horizontal tangent line right there. So the slope of the tangent line, or the slope of the graph is 0. Okay, now let's take a look at part B. It says find G of 1, G prime of 1, and G double prime of 1. So let's start with G of 1 again. And the integral from 1 to 1 of f of t dt. But anytime the lower and upper limits are the same, well, there's no area enclosed between 1 to 1. That's always going to give you a definite 0. And then for G prime of 1, again, we look at the slope. So if we go back to our graph here, at 1, well, if you look at the endpoints here, it's on this line segment right here. This point has coordinates 0, -2. This point has coordinates 3, 4. So we can just find the slope between those 2 points and give us the slope right there at 1. It's just on that linear equation. So we take the difference of the y's, 4 minus 2, -2, over the difference of the x's, 3 minus 0. So you use the slope formula. So 4 minus -2 over 3 minus 0. You get a 6 over 3. So G prime of 1, the slope of that, minus 2. Oops, wait, mistake. This is actually G double prime. Getting ahead of myself. So we're looking at the slope, it's G double prime of 1. So, because we have the graph of G prime, so the slope there is 2, so that's what G double prime was. For G prime of 1, we have the graph of G prime, so we're just looking at the y value. So if we go back here, we put this point again right here, you can see the y value is just 0 there. So G prime 1 is, then for part C it says find all values of x in the open interval -18 at which G attains a relative minimum, and then justify your answer. The relative minimums we find by using the first derivative test. So if we go back to our graph here, we can draw a number line right underneath our graph that represents G prime of x. So label it G prime of x. And what you're going to look at, since this is the graph of G prime, is again the y value. Just like we looked at G prime of 5, we looked at the y value there, and G prime of 1, we looked at the y value. Because this is the graph of G prime x. So whenever the graph is the same as your number line, you're just looking at its y values. In other words, whether it's above or below the x-axis. So you can see the y values start off being positive until -7. So -7. Let's see, the y value is 0. Try to line up your number line directly underneath the graph, so it lines up perfect. And then we can see the y values are negative all the way until 1. For the y value is 0. And then the positive y values all the way until the end of our graph right there in 8. So we're looking for where G has a relative minimum. So this shows you G is increasing here, decreasing here, and increasing. So when the first derivative changes from negative to positive, that's where you have a relative or local minimum. You can see if you're asked for the relative or local maximums, you'd have one right here, -7. So that's when the derivative changes from positive. So now we can say G has, and only ask for the values of x, so we don't need the whiteboard there. A relative minimum at x equals, that's when x was 1. And the way we justify our answer is since t prime of x changes from negative to positive at x equals 1. Then part B says find the absolute maximum value of g on the closing limit from -8 to 8. Justify your answer. So for absolute minimums and maximums, we still use the first derivative. But it's helpful if you could draw a little sketch of the graph. So if we look back here, we saw the graph increasing, decreasing, and then back to increasing. So you can see it goes increasing, decreasing, increasing. So let's sketch what that looks like a little bit here. Increasing, decreasing, increasing. So the absolute maximum, it could either happen at the relative max here, at -7, or it could happen at our other endpoint of B. Those are possible. But so to determine which one it's at, you just have to compare the y values. So we just have to compare g of -7 with g of 8 and see which one is actually larger. So g of -7, just like we found g of 1 here, would be the integral from 1 to -7 f t dt, which again represents the area of the curve. However, notice the lower and upper limits are in the wrong order. The -7 should be down in the lower limit, and 1 should be in the upper limit. So, because -7 is lower than 1. So the way you flip that, remember, is you just put it around negative. And then you change it from -7 to 1. So we got a negative, and then we just have to find, remember this represents the area under the curve from -7 to 1. So let's go back to the graph now. So from -7 right here until 1 right here, we need this area. This, you either find the area of the trapezoid there, or if you split it up, split it into a triangle, 2 triangles and a rectangle. So the area of this triangle is 1/2, this is 3, the height is 2, the 2's reduce, and you're just left with 3, but it's below the x-axis. So any areas enclosed below the x-axis are negative for the definition value of the interval. And we've got a rectangle. Its base is 4, height is 2, so we get 8, but again it's below the x-axis, so it's a -8. And we've got this little triangle here, 1/2, the base is 1, height is 2, so 2 is loose, which gives you 1, but again it's negative. So if you add those up, -3 minus 8 minus 1, that's -12. But we had to flip it so the negatives cancel out now. So we get. Now let's compare that with g of 8. So for g of 8, that'd be the integral from 1 to 8 f t dt. This one we don't have to flip the lower and upper limits because they're already in the correct order. So we now have to find the area under the curve from 1 to 8. We have part of that already. Go back to the graph here. We already know what it is from 1 to 5. So if you keep going there, split this up. we can see this is the same size rectangle, say a quarter circle here. So since this is 8 minus pi, this is also going to be 8 minus pi. And then we just have this triangle right in here. So if we take 1/2, the base is 1, the height is 4, that gives you an area of 2. So from 1 to 8, if we add these all up, 4 plus 8 minus pi plus 8 minus pi plus 2, 4 plus 8 plus 8 plus 2 is 22, and then minus 2 pi. So then we just have to compare which of these is bigger, 12 or 22 minus 2 pi. Well, if you approximate pi to be about 3.14 times 2, that would be approximately 22 minus 6.28, which you can see would be a little less than 16, but that's still greater than 20. So our maximum value refers to the y-value. So now we can say (22 minus 2 pi) is the absolute maximum value of g on the interval broken from -8 to 8. And then to justify it, if you want to do that, then you can just say, since we already sketched what it looks like and we've found these values, it's basically since g of 8, that was one possible place, turned out to be greater than the other possible place the maximum could have been after those negatives. In the last part of this example problem, find the x-coordinate of each point of inflection on the graph of g on the interval from -8 to 8. Justify your answer. So let's go back to the graph now. For points of inflection, that comes from the second root. So now let's draw another nudge line underneath this one that represents the second root. And I'll label it G double prime x. So with the second derivative, since we have the graph of the first derivative, g prime right here, now we'd be looking at the slope, because the second derivative is the slope of the first derivative. So the slope, you can see, starts out being negative. But right there at -7, we've got a corner. So when we have an abrupt change in the slope like that, that's where the derivative of slope does not exist. So at -7, does not exist. And then we can see the slope stays negative until we get to -4. -4, we've got another corner, abrupt change in the slope, so it also doesn't exist there. And then the slope is 0 until we get to 0. Or we get another corner, so it doesn't exist. And then the slope is positive until we get to 3. We have another corner there, so it does not exist. And the slope is negative until 5. This time it levels off here. It's not an abrupt change, it's a nice smooth curve. So the slope there is 0. 5. And the slope is positive until 7. Another corner there, so it doesn't exist. And then the slope is negative. So what this shows us about g of x is the concavity. So you can see here it's concave down still. Since it's not positive or negative, 0, this is just linear, it's a straight line. And concave up, concave down, quantitative up, quantitative in. So we asked to find points of inflection. Those are points where the second derivative changes sign. So it doesn't change to -7, -4, it changes to -0. From 0 changes from 0 to positive, so that's really matter. And at 3, that's the first point of inflection we have. Changes sign. At 5, it also changes sign. And at 7, it also changes sign. So those are the x coordinates where the second derivative changes sign, so that's where we have the points of inflection. So we can say G as points of inflection at x equals 3, x equals 5, and x equals 7. And the way to justify that, and the reason why we knew those were points of inflection, is since G double prime of x changes sign at x equals 3, x equals 5, and x equals 7. Let's take a look at another example now. Here this one says the graph of f consists of 4 line segments, as shown below. Let h be the function given by h of x that go from 0 to x of f of t dt. So let's find h of 2, h prime of 2, and h double prime of 2. It says for each of those, find the value or explain why it does not exist. So let's start with h of 2. So for h of 2, all we need to do is plug in 2, substitute in the 2 for the x, so it'll be from 0 to 2, f of t dt. And again, we have the graph of f of t, or f right here. So we want to go from 0 to 2, so that would be the area of this triangle right here. So that's 1/2, the base is 2, and the height is 3. The 2's reduce out there, so you just get 3, but it's below the x-axis, so it's negative. And then to find h prime of 2, well, we need h prime first of all. So if we take the derivative, h prime of x, then we should take the derivative with respect to x of this side of the equation as well. Go from 0 to x of f of t dt. You can see again that this fits the second fundamental theorem of calculus. It's the derivative of an integral, and the lower limit is a constant, the upper limit is x. So the derivative and integral essentially cancel out there, and we get h prime of x equals, the x just replaces the t, f of x. So again, we know this was the graph of f, and h prime is equal to f. So this is also the graph of h prime of x, which we're. So for h prime of 2, since this is the graph of h prime, we would just be looking at the y values. So the y value right there, 2, you can see is 0. And finally, for h double prime, of 2. Well, for h double prime of 2, then we'd be looking at the slope. Because h double prime is the slope of h prime. But notice at 2, you've got a corner there. So the derivative or slope doesn't exist there. We have an abrupt change there. So we can say h prime of 2 does not exist. We abbreviate that EME. And notice it says find the value, like we did here, or explain why it does not exist. So the way to explain or justify why it does not exist is since, here's where you use limits. So it's the limit as x approaches to, from the left, of h double prime, which is the slope of h prime. That left-hand slope there does not equal the limit as x approaches 2 from the right of h double prime. Now for part B, it says for what values of x in the open interval -4 to 4 is h decreasing? Explain the reason. So the graph is decreasing. That comes from the first vertex. So you have right here. So if we put a number line in right underneath here. I'll label it h prime. So that's what this is the graph of. And we'll be looking at, and this is right h prime. So whenever the graph is the same as your number line, you just look at the y values. Okay, so the y values start off being positive until -2, 0. Then they're negative all the way until +2, 0, and then back to positive. So what this shows us about h is it's the slope of h, so h would be increasing here, decreasing. So now we can answer part B. You can see it's decreasing between -2 and 2. So h is decreasing on the interval -2 to 2. And explain the reasoning, you can say since h prime of x, first derivative, is negative, less than 0 on -2 to 2. For part C, it says for what values of x in the open interval -4 to 4 is the graph of h concave down, and explain the reason. So, where it's concave down, well, concavity, we determine that based on the second derivative. So now we need to draw another number line underneath our graph here. But now it's going to represent h double prime x. And since we're looking at h double prime, and this is the graph of h double prime is the slope of h prime, so now we're looking at the slope. So you can see the slope starts off being negative until -2. Well, we've got a corner there at -2, so it does not exist there. And then the slope stays negative until 0. Or again, we've got another corner, so it does not exist there. And the slope is positive until 2. Another corner, so it does not exist. And then the slope is positive. So, whereas the graph concave down is when the second derivative is negative. So let's see here, it's concave down, concave up, and concave up. And because it doesn't exist at -2, we do have to stop under our interval there. So we can say h is concave down on the intervals -4 to -2 and -2 to 0. And to explain the reasoning, it's since h double prime of x is negative or less than 0 on these intervals, -4 to -2 and 3 to 2. Now let's look at part D on this one. It says on the axes provided, sketch the graph of h on the closed interval from -4 to 4. Okay, so let's see what we know about the original function. So we know right here h of 2 equals -3. So that's a point we know for sure on the original function. Let's go ahead and plot that one first. We know that it goes to the point 2, 3. Or 2, -3. From right here. So we can start with that. Now you could find a whole bunch of points here, just like we did for h of 2, but there's an easier way, and that's to recall that the definite integral, or the area between the curve and the x-axis of the derivative, not only represents area, it also tells you the change in the original function. So, in addition to that, we can use our number lines here. So look at the increasing, decreasing intervals and the concavity. So if we find the area of this little triangle right here, 1/2 the base is 2, the height is 1. So the 2's reduce that, you can see the area down the triangle is 1. So from the number line, we can see that from 2 to 4, h increases right here. And the area tells us, of 1, tells us exactly how much it increases by. So since it was a -3 here, we know that it increases by 1, so at 4, it's got to be up at -2. Because it increased by exactly 1. So we can get a very accurate graph here based on that information. Whereas previously, when we had to graph the first derivative, if we didn't know these exact areas, then we just kind of have to guesstimate what the y value would be. So, but here we know exactly what it is, so we can say from 2 to 4, it's increasing, concave up, using our shape like a cup. So, increasing, concave up like that. And then we can work our way back here. We already know the area between 0 and 2 is -3, and that shows us exactly how much it decreases by. So if it decreases by 3 to get to -3, it must have started 3 above that. So at 0, it must have started up here at 0. That way when it decreases by 3, that's what will get us to -3. And we can look at our number line and see from 0 to 2, it's decreasing, concave up, shaped like a cup. So we'll go that. Decrease, whoops. Try our best to level it off there at 2, because we know at 2 the slope is 0. Then keep working back, and we can see this triangle is the same exact area as this triangle, so it's also -3. So from -2 to 0, it also decreases by 3 again. It's decreasing. So if it decreased by 3 again to get to 0, it must have started up here at positive. So from -2 to 0, it's decreasing, concave down, shaped like a fret. So decreasing, concave down, like that. And the final interval, we can see this triangle has the same area as this one. So it's also got an area of 1. So that means it increased by exactly 1 to get to that point. So it increased by 1 to get to 3, it must have started here at 2. And we put our number line and see, okay, it's increasing, concave down, shape like that. Again, you can see it levels off right there at 2, or -2. Because the slope there at -2. So using the number lines to see where it's increasing, decreasing, and concave up and concave down. And in addition to the areas under the curve of the first derivative, you can get a pretty accurate graph of what it looks like. And for part E, it says, suppose that f is defined for all real numbers, x, and is periodic with a period length of 8. So periodic, remember just like sine and cosine, the trig functions, that means the graph keeps repeating over and over again, looks the same way. And the period length tells you how often it repeats, in this case, every 8 units. So the graph shows one period of f, So you can see from -4 to 4, that's 8 units in width there. So it keeps repeating this same shape over and over and over again. So it says first, given that h of 4 is -2, find h of 12. So let's start with that part. So when you have a point on the original function, you're looking for another point, but we don't know how the equation, we have the first derivative information of that. That's one of those initial plus change problems. So h of 12, the initial value we're given is h of 4, we know it's -2, plus the change comes from an definite integral from where our initial value is 4 to where we're looking for it at 12. We want to know how much does the function change from 4 to 12. And what goes right here, the change is just the derivative of whatever this function is. In this case, h prime x. Because remember, the definite integral of the derivative tells you exactly how much the original function changes. So h of 12, h of 4 we're told is -2. And then plus, well, from 4 to 12, you can see that's just 8 units wide. That's one more period. Oops. So it's going to look identical to this from 4 to 12, starting from right here, as it did from -4 to 4. So if we add up all those areas, 1, -3, -3, and 1, that'll give us how much it changes by. So you can see it's -2, that's -4, h of 12 is -6. So it changes every period, it basically decreases by 4 units. So that's the first thing we're asked to find. The next thing we're asked to find is to write an equation for the line tangent to the graph at x equals 85. So for x equals 85, if you want the tangent line, we need two things. We need the point of tangency and the slope. So let's start by finding the point of tangency, similar to how we did this one here. So we want to find h of 85. Well, the initial point we're given is h of 4. Plus the change this time will come from the integral from 4, where our initial is, all the way to 85. H prime x. So again, we know the initial value we're given, h of 4, we know it's -2. But this time, to go from 4 to 85, well, we need to figure out, well, how many periods does that represent? The period length is 8. So the way to figure out how many periods it represents is just to subtract up the lower limit from the upper limit. So if we go 85 minus 4, we get 81. That's the width of this interval. And then divided by the period length is 8, we get 10 and 1/8. So that allows us to split this up and say, okay, well, we know this is 10 of the exact same interval. It's going to look identical. Every period, remember, looks the same thing as it looks from -4 to 4. Because it's periodic, it's going to look identical to that. From -4 to 4. Of x dx. But there was one left over. So the one that's left over is basically that interval from 84 to 85. That's that last little one that's not part of the 10 periods. Okay, so let's keep going there. 85 by negative 2 plus 10. And we already figured out from negative 4 to 4, the same as from 4 to 12 here, one period, remember that area under the curve equals negative 4. So it's 10 times negative 4. But from 84 to 85, because it's periodic, we go back to the graph here, that's going to look identical to what it is from negative 4 to negative 3. Because we have that one remainder. So it goes through 10 periods and then one more. So from there to right there. So it's the same as it is from negative 4 to negative 3. Well, just like that. It's periodic. So again, negative 2, 10 times negative 4, negative 40. And then the area under the curve from negative 3 to negative 4 to negative 3, look back and see, okay, well, it's this little trapezoid here. So if we use the trapezoid formula, area is 1/2, the width is 1, times this height is 1, plus this height is just 1/2 right there. So you get 1/2 times, that's 2/2 plus 1/2 is 3/2, gives you 3/4. The area of that little trapezoid right there is 3/4. That's the area of the curve. So we get h of 85 equals negative 2 minus 40 is negative 42 plus 3/4. If you get a common on there, 4. Okay, well that's negative 1 multiplied by 4, 168 over 4. Plus 3/4 gives you negative 165. So that's our y coordinate at 85. So what we've just found is the point of tangent. So we know 85 is negative 165 over 4. The point of tangent C. So now all we need to know is the slope. So we need to know what h prime of 85 is. So again, just like we did the other one, we're just looking at the y value. And we know 85. Remember, the interval from 84 to 85 looks identical from negative 4 to negative 3. So 85 is going to be in the exact same place as negative 3. And you can see that y value is exactly 1/2. So y value. So that's the slope of the tangent. Okay? And that's all we need. So now we can write down our tangent line. Y minus the y coordinate, which is negative 165 over 4, so the negatives cancel out, which is plus 65 over 4, equals, the slope was 1/2, times x minus the x coordinate. Now let's take a look at one more example here. This one says the graph of the function f below consists of a quarter circle, right here, and 3 line segments. Let g be the function given by g of x equals the integral from x to 4 of f of t dt. So it says find the average rate of change of g on the interval from, oops, that's part C. Let's start with part A. Find all values of x in the closed interval from negative 4 to 6 for which g of x equals 0. Well, here's g of x. We want to see what makes this equal to 0. So we're really looking for, where is this integral from x to 4 of f of t dt. What values of x would make this definite equal to 0? Sorry about that, I wrote that 0 twice. So let's start out with the obvious one. Well, the obvious one is if this lower limit is the same as the upper limit, if it's 4, then that's what always makes a difference. So the x equals 4. Now let's see if there's any anywhere else. Well, since that makes this definite equal 0. Well, you have to look at the graph and understand this definite integral represents the area under the curve. So basically it stops right here at 4. So if we put 5 or 6 there, we can see, well, that area wouldn't be 0 there. If we put 3 there, that wouldn't be 0. If we stop there at 2, look what would happen. Let's see the area of this triangle. 1/2 base is 1, height is 2. It's positive 1. This is the exact same size, except it's below the x-axis, so it's negative 1. So if you integrated from 2 to 4, you can see the negative 1 and 1 would cancel out, leaving you with 0. So 2 is another answer, another x coordinate, where it would make this definite fully equal to 0 if we integrate from 2 to 4. Let's keep working back here, see if there's anywhere else. Notice if we stop right here at negative 2, the area of this triangle, 1/2 the base is 2, the height is 2, gives you positive 2, and this triangle is the exact same size, but it's below the x-axis, so it's negative 2. So the same thing would happen. 2, negative 2 would cancel in addition to the 1 and negative 1, so the overall definite integral from negative 2 to 4 would also be 0. So x, the lower limit, could also equal negative 2. We work back here, that's the only time where the area is below the x-axis. Above the x-axis we cancel. So there's 3 answers, 4, 2, and negative 2. So it's just a matter of understanding this definite integral again represents the area under the curve. Okay, so for part B, it says find the x-coordinate of each local maximum g on the open interval from negative 4 to 6. So for local maximums, we need the derivative. So g prime of x, the derivative of this integral, x4 after t dt. But notice something a little bit different this time. This time it doesn't fit the second fundamental theorem exactly. The reason why it doesn't fit the second fundamental theorem exactly is because the lower limit is x and the upper limit is a constant. It should be flipped around the other way. So the way to resolve that, remember if you want to flip lower and upper limits, you just take out a lot of negative, make it the opposite sign. So this time, g prime of x doesn't equal f of x. It equals, because we had to flip it, negative the opposite of f of x. So this is the graph of f of x right here. So the graph of g prime is the exact opposite of f. So what it would look like is where f is positive, g is going to be negative. It's just going to be basically flipped or symmetrical about the x-axis to f, because when it's positive it becomes negative, when it's negative it becomes positive. So let's try to sketch the graph of that. So here would be this quarter circle down here. Then instead of this one, the positive values, it would be these negative values right here. And instead of this segment, it would be up here like this. Negative values would be positive. Instead of these negative values, it would be these positive values. With these positives, it would be these negatives. And instead of 2 there, it would be negative. So this is the graph of g prime of x, not the original one we were given. It's a little bit different. So using that graph, we could draw a number line right underneath this. And I'll label it g prime of x, since we're looking for local maximums. So g prime of x, we've got positive values, and we look at this is in green here. This is the graph of g prime. We look at the y values. So we've got kind of negative, and one greener. Negative y values until 0, and then we've got positive y values in green there until 3, towards 0, and then negative, the rest of them until south. 6. So now we can see that g of x will be decreasing, increasing, decreasing. So we can see we have a local maximum right there at 3. So I can say g has a local maximum at x equals 3. And then to justify our answer, it would be since g prime of x changes from positive to negative at x equals 3. Now for part C, it says find the average rate of change of g on the interval from negative 2 to 3. So first there's that keyword average. Whenever you're finding the average of a function on some interval, in this case from negative 2 to 3, first thing you have, remember, is the 1 over b minus a on the in this case, a is negative 2 and b is 3. Let's start off with 1 over b minus a, so 3 minus negative 2. And then after that, you have the integral from a to b, in this case from negative 2 to 3. And what goes inside the integral is whatever you're trying to find the average of. But read carefully. When I find the average of g, we find the average rate of change of g. Rate of change, remember, is another word for the derivative. So it's the average derivative of g, which is g prime. So that's what we're really finding the average of. So that'd be 1/5 on the outside. Now, there's two ways of doing this. One way you could do this was actually integrate g prime. That would give you g, and then plug in 3 and negative 2 into g. But there's actually an easier way. And that's to remember we've got the graph of g prime right here in green. So this just represents the area under the curve from negative 2 to 3. So from negative 2 right here to 3 right here. So the area of this triangle, if this one was 2, this one would be negative 2. And since this one down here is negative 3 altogether, this would be a positive. So that would be negative 2 plus 3, which is just 1, times 1/5 gives you 1/5. So that's the average value of the derivative, or average rate of change of g on the interval from negative 2 to 3, so 1/5. And then part D relates directly to that. It says for how many values c, where c is between negative 2 and 3, is g prime of c equal to the average rate found in part C. So we're looking for where does g, how many times, between negative 2 and 3, does the derivative, g prime of c, equal this average value we got of 1/5. We know it has to equal at least one time, since that's the average. We've got a continuous function here. So the way to tell is just think, well, we've got the graph of g prime in green here. So we're basically looking on the interval from negative 2, right here, to 3 right here. Well, 1/5, you just graph that 1/5 is right here, right? Well, so from negative 2 to 3, how many times does g prime equal 1/5? Well, we can see it intersects right there once, and right there one more time. So we can say the answer is 2. There's 2 values of c. And it'd be since, different ways to justify this, but Simplest way would be to just say, since the graph of g prime of x intersects the line y equals 1/5, which is what I got there, 2 times on the interval from a to 2. See right here, it did intersect the 2 times. Then part E says find all the intervals on which the graph G is concave up. Explain the reason. So if we go back to the graphic, concavity again comes from the second derivative. So if we draw our number line here for the second derivative, label this G double prime of x. Again, since we have the graph in green here of G prime, we'll be looking at the slope. You can see the slope starts off being negative until -2, where it does not exist. And the slope is positive all the way until 2. Got another corner there, so it does not exist. And then the slope is negative until 4. Another corner, so it does not exist. And finally, it levels off the slope, which is 0. So we're asked to find where is graph concave up. So concave up is where the second derivative is positive. So here it's negative, so it's concave down. Then it's concave up, concave down, and then with 0, that's just a linear, just a straight line. So it's concave up from -2 to 2. So we can say G is concave up on interval -2 to 2, and explain the reasoning. Since G double prime of x is greater than 0, off interval -2 to 2. And that concludes the notes on the topic of the second fundamental theorem of calculus.